This problem, problem 3, is a little bit different. For this problem, we have a simple pendulum, which is a string, and there is a small object attached to the end of this string. This object has mass m, and the length of the string is L. At time moment 0, this object will be displaced at a small angle, and we will count this angle from vertical. This will be small angle, and this will be the object now at angle theta naught. And this angle theta naught is a small angle, such that we can use small angle approximation. Sine theta is approximately equal to theta. So at time moment 0, I bring this object at angle theta naught, and then I let it go. So what I want to find, as always, I want to find the position of this object at any time moment. Theta is a function of time. And this will be harmonic motion again. So it will go back and forth, and angle is small, we will use it. So now I want to start with some equation, because we know what we need to do. We need to derive the equation of harmonic oscillator. So which equation I will start with? Before that, we always used second law in the form f sub x is max. Now I will start with the equation tau external. External torque is I alpha, right-hand rule. It obeys right-hand rule. My positive direction of rotation will be counterclockwise. You see my mirrored image. So the angle increases in counterclockwise direction. So positive direction of rotation will be out of the board. This is my coordinate system with positive out. Now I will draw the forces. Which forces are acting on this object? They will provide torque. I will write torque created by these forces. One of them obviously is mg, another one is tension. I will write torque about this pivot point O. If this is my pivot point, then torque created by tension is 0, because R torque is R cross F. So R from the pivot to the point will be parallel, or in this case, anti-parallel to force. So torque created by tension is 0. What is torque created by gravity? Well, we need to figure it out. I will draw the line perpendicular to vertical, because for torque, it's cross product. We are looking for perpendicular components of R and force. Force of gravity is down. R is from the pivot to the point where the force is applied. Let me draw R. I will use, let me see what is left, red. R will from the pivot to the point where the force is applied. This will be my R, and I'm looking for component of R that is perpendicular to gravity, which obviously is this. And this leg of this right triangle is length hypotenuse is L. I will erase 0, because this is not my initial condition. This is supposed to be any angle theta. This will be true for any angle theta. This length will be L times sine theta. That's what we need. And I'm ready to write the torque. Torque created by gravity, magnitude of torque, will be mg, force, and then this leg, L sine theta. Now I need to figure out direction. I need to know, is projection of torque on my axis is positive or negative? And to do it, as always, I will start force and R from the same point. Force is vertically down. I start R, I move it, I start it from the same point. This is R. And now I need to figure out cross product R cross mg. So you use your right hand. I will use my left hand because you see my mirrored image. Let me do that. Let me try. So from R to mg, what will be the direction of the torque? It will be into the board. Direction of torque is into the board. And my positive direction of rotation is out of the board. So projection of torque is negative. I put minus here. And this is equal to I. I, moment of inertia, is mr squared. M is m, and r is L squared, times alpha, angular acceleration, and angular acceleration is second derivative of angle, d2 theta by dt squared. Now I use my small angle approximation. Sine theta is approximately theta for small angles, and we solve this problem only for small angles. What I get is minus mgl theta is equal to m L squared d2 theta by dt squared. Now if I divide both sides of this equation by L, I divide both sides of this equation by L, and then next, give me 1 second, and next, what I will do next, I will divide by M. And now I bring everything on one side of the equation. It will be L, and then it is d2 theta by dt squared plus g times theta, and this is equal to 0. Look at this. I divide by L, and what do we get? We get the equation of harmonic oscillator, d2 theta by dt squared plus g over L theta is equal to 0. Different problem. We even started with different equation, and we derived the equation of harmonic oscillator. Now we know what to do. All we need to do, we need to find the solution of this equation. And as always, I guess the solution of this equation, second order differential equation, I guess the solution as A cosine omega t plus B sine omega t. Well, I need to find A, B, and omega. Do we know omega? Yes, we already know omega. What is omega? It is this guy. This is omega squared. But first of all, let's find A and B from the initial conditions. You know what? I forgot to write the initial conditions, which is not a good idea. I will do it right here in red. What were my initial conditions? Theta at time moment 0 was theta naught. And velocity, and in this case it will be v theta. And velocity at time moment 0 was 0. I just let it go. These two equations are my initial conditions. Okay, we keep going. Theta at time moment 0. I plug in time moment 0 here. Cosine 0 is 1, so I have A. And, second one, sine 0 is 0, no second guy. And this is equal to theta naught. We already found A, great. Now I need to find B, and for B I need to figure out what is my velocity. Velocity, v theta, is r omega. Remember, v theta is r omega. What is r? It is L. What is omega? It is d theta dt. So I need to differentiate theta to find d theta dt. Let's do it. It will be minus A sine omega t, omega, chain rule, and then plus B cosine omega t. And chain rule, again, will give me omega. This is my velocity. And now I need to plug in my initial condition. This is velocity at any time moment. Now I plug in initial condition. Velocity at time moment 0. Let's do it. L, and then in parentheses, I have, well, no parentheses, sine 0 is 0, cosine 0 is 1, so I have, that was not a good idea. I have L, and then this is 1, so I have L B omega. And this L B omega is equal to 0, which gives me B. B is 0. Okay, now we know A, we know B, all is left omega. That, well, we already know, but I want to do it again. So I rewrite my solution now, everything that we know. Theta as a function of time is equal to A, which is theta naught, times cosine omega t. And we already figure out that B is 0. Now I take this, I bring it back into my equation. The first derivative is, let's do it real quick. D theta dt is minus A omega sine omega t. Second derivative will be d2 theta by dt squared. It will be minus A omega squared, chain rule, cosine omega t. And now d2 theta dt squared goes into this equation. We have minus, can you see it? Yes, minus A omega squared cosine omega t. This is the first guy, plus G over L. I pretend that I don't know what is omega. G over L times theta, which is A cosine omega t. And this is equal to 0. This is equal to 0. This is my equation. Now I divide by cosine. I divide by A. What is left? Well, we have omega squared. We have minus omega squared plus G over L is equal to 0, which gives me omega squared as G over L, or it gives me omega as square root G over L. Now we know everything. We know that theta as a function of time is equal to theta naught times cosine omega t, square root of G over L times time. And if we want to find the period of oscillations, T, period of oscillations, I will write it right here. Period of oscillations, capital T, is 2 pi over omega, or it will be equal to 2 pi divided by omega, which will give me square root of L over G. So the period of oscillations will depend just on the length of the string and acceleration of gravity. And that's it. We found what we wanted to find. We found theta at any time moment.